Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss the concept of effect of acceleration and friction in suction and delivery pipes on indicator diagram. So in the previous lectures, already we discussed regarding this effect of acceleration and friction in suction and delivery pipes on indicator diagram. But that time we have discussed individually. We have discussed the concept of effect of acceleration in suction and delivery pipes on indicator diagram. Again, we have discussed the effect of friction in suction and delivery pipes on indicator diagram. So both are discussed individually. And initially we have discussed about the ideal indicator diagram. All these things are already discussed, but at this condition, this effect of acceleration and this effect of friction was combined on the suction and delivery pipes. And this is the diagram of given. So in the x-axis we have this stroke length. This is the stroke length in the x-axis, and in the y-axis we have the pressure head. Is the pressure head the y-axis. So before going to explain this diagram, let me just give a brief intro about this working of this reciprocating pump. This is the diagram of reciprocating pump, and in the diagram already I have explained previously many number of times. This is the cylinder part, and this is our valve. So this is the delivery pipe, and this is the delivery valve. And meanwhile, in this inside the cylinder, we have this piston is there. The piston is connected with the help of piston rod to the connecting rod, and the connecting rod is connected to the crank. So this is the closed piston is there, and this is our suction valve, and this is our suction pipe, and this point is cylinder. Okay, and this is our piston. And now if you see here this piston rod, connecting rod, then this is the crank. So the crank will be started with the help of motor, and it will be started rotating, and it will create a circle like this. Okay, so this is the movement of the crank. So at this position, the starting position, when the piston is the left side, so it is in the normal condition, like before starting the pump. So at that time our crank is making an angle of 0 degree. Okay, now when it will start rotating, the crank will start rotating, so the piston will be start moving from the left side to right side. So in between, so this is the middle position, and this is the left like we can say right side position. So at this middle position, the crank will make an angle of 90 degree here. Okay, and at the end of this position, that means at that time the crank will be 180 degree. So this is 180 degree, this is 90 degree, and this is 0 degree. Again the crank will be started rotating reverse direction. So this is forward direction, this is reverse direction. So this is suction stroke, this is delivery strokes. So all these things we have already discussed in the previous lectures. So you can consider 0, 90, 180, 270, 360. Or else if you want to again conclude here, starting from here delivery 0, 90, 180 also we can consider here like this. Okay, so this is the working of this. Now previously we have discussed, so here I'll show you the diagram. This is the diagram actually for the ideal indicator diagram between the pressure head and the stroke length. So stroke length is nothing but the distance which is traveling by the piston inside the cylinder. This is the distance if it's traveling by the piston, then that is the stroke length. So here if you consider, this is our stroke length, that is L. Okay, so here this part is only, this side is R, and if I write R equal to our L by 2, total length by 2, that we know. So yeah, this is the stroke length, and this what diagram I have shown you, like A, B, C, D, this is the path or the diagram for the ideal indicator diagram we have discussed. And this incline line what you are seeing, like I show you, like A dash, B dash, C dash, D dash. So this is the path for the effect of acceleration during the for the suction delivery pipes. And this curvical structure, the curved structure what you are getting, previously we used to get like this only during the friction, but when it is combined both acceleration and friction, see only friction time we got this diagram like this. Okay, if you see our previous lecture, there you can see this is the diagram we got here, a parabolic structure like this. Okay, but as we have combined both of the things, like friction and acceleration, that's why we got the diagram. That's why I'm going to explain here. So okay, so one condition we'll see. The first condition at the beginning of the suction stroke. So we'll start about the first suction stroke, then we'll go for the delivery stroke. So first we'll discuss about the suction stroke. The suction stroke, as I told you, 0 degree, 90 degree, 180 degree. That means the piston started moving from the left to right. So at the starting of the suction stroke, the theta will be 0 degree. Okay, and theta will be 0 degree, so that okay, this pressure head due to the acceleration at the suction, we have already derived this one, and we got the equation for this, like Ls by G plus A by As, this is omega square R. So here this is the formula, as I told you, at this point theta equal to 0. But if this is the condition theta equal to 0, then we'll get HFS also. Okay, so this is the equation. Now for the pressure head, at this point our Fs equal to 0. At this point, at the suction stroke, theta equal to 0, this is the value, and HFS will be 0 here. So the pressure head in the cylinder will be like HS plus, we can write this is HS into, sorry, plus HS. That means acceleration due to the pressure head and the suction head. If you see that one, this is our suction stroke. This is our suction stroke, right? This is suction stroke, and this side actually delivery stroke. Okay, when the suction stroke, if you see at the inlet of the condition, like this is the suction head HS, and this is our delivery head, and along with that, this acceleration due to the pressure head was added, and acceleration due to the pressure head due to the acceleration at the suction was added here. Okay, so at the inlet of this, HS plus HS will be added here for the suction stroke, and that will be below to this, and this is the atmospheric pressure head. Okay, the value of this is 10.3. This also I told you like how to calculate. P equal to rho GH, and then H equal to P by rho G. P value like 1 lakh something will be there, and 1000 into 9.81. So by that we calculated the value of H equal to 10.3, and that is atmospheric pressure head. Okay, so now what I mean to say here, this value of this addition, okay, this is below the, this is, if you see, below the HATM. Okay, that is below this value. Now this is the first condition. Now the second condition, if you see, same at the suction stroke, this is, let me write, beginning. This is the beginning of suction stroke, and next, right, at the middle of, the second condition, at the middle of suction stroke. Yeah, so what will be the middle of the suction stroke? At that time our HAS will be 0. HAS will be 0 here. Okay, so middle of the suction stroke is nothing but that is theta equal to 90 degree. So theta equal to, at this point, 90 degree, and this is the value. This is HFS is the loss of head due to the friction. Okay, and this is the pressure head due to the acceleration in the suction pipe. So theta equal to 90 degree here. Now here HS value is 0, and HFS equal to, this is 4FL LS. So you can write here, this is DS 2G, this LS DS because of the suction. Okay, and the value of this A by AS, and this is omega R square. So this is the value of HFS, and this is AS. And now the pressure head and in the cylinder will be, so the pressure head will be, so here we can write the pressure head in the cylinder, that can be written HS plus HFS, HS plus FS. That means at this point, if you see, this is the point from this middle point, because this is 0 degree, this is 90 degree if you consider, and the end of this is 180 degree. The suction stroke started here, this is the middle point, and this is the end of the suction stroke. Now we'll go for the next one. So if you see, this is the value of HS plus HFS. So this also, like this is also below the, H atmospheric. Okay, and the third condition is at the end of the this is initially middle, now at the end of suction stroke. This is end of suction stroke. Let me write in the short form. End of suction stroke, we can write the same thing. Again, we need to find at this point what is the effect of acceleration here. So at this point, acceleration HAS will be minus. So that is because there actually sin theta and cos theta, different values are there. If you put the value of theta value, we'll get here minus here. So that is actually these things already we have found previously equation. That's why I'm writing directly here. Okay, and this is LS, again same thing will be there, like G into A by AS, and this is omega square R. This is about the HAS. And similarly, again we need to find out the HFS. So the HFS will be friction due to the loss of head due to the friction to the suction. At the end of this suction stroke, this will be 0 here. So why it is because 0? Because at the end of the stroke there will be no flow. No flow means no friction, no, that's why 0. At the starting of this also same thing. At the starting of this, that is there is no flow is there, it is in silent condition. So that's why the friction, there is no friction, and that's why we got here HF is equal to, there is no loss of head. That's why it is 0. Okay. Now same thing I can write here, the pressure head in the cylinder. Again same thing, the pressure head in the cylinder. We can write this. Here will be HAS. What is the suction head is there? How much suction head is there? This minus is the negative. So that will be minus of this HAS. And this value also will be below the atmospheric head. Now see this point. This is the total height. HS was there. HS is there. Now here HAS is going to minus here. So minus if you do, you'll get this value. So this is first starting point. This is ending point, and second point, the middle point, we got this one. If you join this, then we'll get a curve like this. Okay, so this is also below the atmospheric pressure head. Okay, so this is all about the suction stroke. Okay, this is all about the suction stroke. Now we'll see about the delivery stroke. So similar manner, we can write about the delivery stroke. In the delivery stroke, if you see, this is at this point, like at that once suction stroke completed, then again it will be back to this delivery stroke. So this is our delivery head, and this is our that pressure head due to the acceleration at the delivery pipe. Okay, so for the delivery stroke, again we'll start one by one. Like for the beginning, similar way, at this beginning of the delivery stroke. So that means, let me write initial, or we can write the beginning of delivery stroke. For the beginning of the delivery stroke, we can write beginning of delivery stroke. We can write. So just I'll change the wordings here. HAD, here HAS, here HAD. So this will be like the same value. Only we'll get a minus here. This is LD by G into. This is not plus. This is into, actually, not plus. Yeah. Next is here A by capital A by small a d, and this is omega square R. But here if you see, this is about the pressure head due to the acceleration at the delivery pipe. But what about the friction here? The friction at the starting point will be 0, because there is no flow. There is no flow means there is no loss of energy, so, or no loss of head. That's why here it is 0. So here if you see the pressure head in the cylinder, so again we can write here the pressure head in the cylinder, which is above the, like this is when we can write HD. Okay, this is HD plus. Here it is minus we got because it is like this is the value was there. It was total height. This suction head was there. From that again it was reversed. That's why minus was it. But here if you see HD plus HAD, so that means our total height is HD is this one. Again this much height was added to this one due to the acceleration. That is that head. So this will be the value, and which will be above, of H atmospheric. Okay, so this is the first point. Similarly, again we need to find out the middle of this suction stroke. Similarly, again let me write here. Yeah, this is the middle. The next point is the middle of delivery stroke. In the middle of the delivery stroke also we can write here. Here will be acceleration part will be 0. So HAD equal to 0, and the value of HFD will get a value like 4F. This is this equation actually we know that due to the loss of head due to the friction, that is known as Darcy-Weber's equation. From that only it was derived. Okay, on behalf of V, we written this equation. So this is also same thing, like 4f L d square. This is d into d. This is 2g, and capital A by small a d. This is omega r square. So here also, if you see, the value of pressure head in the cylinder will be hd plus. Here also we can write hd plus, will get hfd. hd plus hfd will get here. Okay, and that also will be above the atmospheric pressure head. This also above the H ATM. Okay, so here also we got the above atmospheric pressure head, and here also we got the value above the atmospheric pressure head. That means at the middle of this, you can see this point. Okay, so how much is there? This much distance is there. This is the middle of this. So next one at the end of this. So the end of this will get, now see, this is the total height was there, HD. Now if you see, this much was going to subtract from here. Okay, so that is going to be minus here. So that means HD minus HAD. So that it will be end of the delivery stroke. So let me write the third point. The third point is, you can write end of delivery stroke. So end of the delivery stroke, we can write, again the formula we need to write here, that is HAD equal to minus LD by G into, again just A by capital A by small d, and this is omega square r. This is about the head. And what about the friction? So here friction, there is no friction because end of the stroke. So this will be 0 here. So the pressure head we can write here. So we can write the pressure head in the cylinder will be, in the cylinder, though it is below this one. So we can write this HD, the delivery head, minus, will get the value of this one. Okay, and this also will be above the atmospheric pressure head. So you can write H atmospheric. Okay, so all these things we got here. Now the same thing, if you see in the diagram, the same thing was mentioned here. Already I told you previously, this is minus at the end of the delivery stroke. This is starting of the delivery stroke, middle of the delivery stroke we got here, and this is end one. Similarly here also, starting of suction stroke, middle of the suction stroke, end of the suction stroke. Now if you plot all these diagrams, then you get this. So let me draw this one with some different color. It will be started from here, and like we continued up to here. Then again it will become to back to this position. Then again it will be here. So all this way we can cover this diagram. So here, if you want to represent this area of this plot, so we can write the area of these things, like in the indicator diagram, if you see, because all these shapes are different. So here in the indicator diagram, with the acceleration and the friction, just I given here, so we can write the area, because areas are different, you can see. So the area of the indicator diagram, so let me write this indicator diagram. So area of indicator diagram. So what are the points are there? Let me remind once again. This is A dash, B dash, this is G, G dash, and here C dash, this is H, H dash, and D dash. You just need to remember these points for this further explanation. So area of indicator diagram, I can write here. This is A dash, G, and B dash, A dash, G, B dash, and along with this also like C dash and H and D dash. Okay, this is area of indicator diagram if you write. So this one we can write the area of A dash, G dash, B dash, again along with the C dash, H dash, and D dash. This plus area of the parabola which is created, area of parabola which is created, that is nothing but A dash, B, G dash, plus again the area of parabola in the delivery stroke. This is suction, and in the other side also we have the delivery. So area of parabola, that is nothing but C dash, H, and DS, I hope. Yeah. So let me again See here. Now see what I have taken here. A dash G B dash, again C dash H dash D is total. Okay. Along with that, this one A dash G G dash. No. Here what I have written here. A dash G. Yeah. A dash, G dash and B dash. Okay. This one. Again this parabola. Okay. That's why two parabola area I have written here. This is one parabola A dash G B dash and C dash H D dash. Okay. Now, but the area of this, if you see, this is the area is nothing but what you have seen. I told you previously also we have done this one. So area of the this line is nothing but, I'll write first this one. So the first one is area of A dash G B dash, like A dash D dash B dash C dash H dash and D dash. This is nothing but the same area we can consider for the area of ABCD. Area of ABCD, if we write in this way, we'll get, if just again one more, so you see, this is the area is nothing but ABCD area. So ABCD area is nothing but just we have tilted this one because of the friction and this acceleration. So we can write this one. So on behalf of area of ABCD, what we can write? This is nothing but the distance of suction head to the delivery head into the stroke length, that is L. So this is the area of this. Now similarly, we'll go for the area of parabola. So next one, the area of first parabola. Parabola of which one? A dash G B dash. So area of parabola, that is A dash G B dash. So here also we can write like the base into height. So here you can write A dash B dash into, and here this is 2 by 3. 2 by 3, what is the value was there? Yeah, this is G dash into this one. G dash into this one, we can write I. So let me write here A dash B dash into G dash into I. Okay. So here I can write this is like A dash B dash. So on behalf of A dash B dash, what we can write? Okay, let me write here, then we'll see. And this I place in the sense the total perpendicular line, that one. So here we can write G dash actually. Okay, A dash B dash. Okay, let me check it again once. Okay. So here if you see the G to I point, this is there actually. Okay, similarly at the delivery stroke also we have given H dash to J. Okay, so that's why I have written there G to I. Okay, now if you see this is the G point, this is I point. Okay, and this is our G dash point. Okay, so here also the same thing I have written here, A dash B dash, the area of this one, A dash B dash by into 2 by 3 G dash I. Okay, and here again we can write this is 2 by 3 into A dash B dash into G into I dash, and again this form we can reframe it like 2 by 3 into AB. So A dash B dash is nothing but AB we can write, and here we can write again G dash. Okay, G here if you see that GI value like G dash to I. Okay, what is the distance is there? That is nothing but G to G dash. Okay, so this is the value for the this, and here if you want to put the value of AB, I can put it here like 2 by 3. What is the length of this AB? That is nothing but stroke length. So here you can give the like if you want to give it L dash, you can write L dash, and the GF dash is nothing but HFS. Okay, so this is the area of the parabola for this one. Similarly, for the delivery stroke also we need to find out area of parabolic, that is C dash H and D dash at the other side. If you see, that is the delivery stroke side. Similar way we can find out, and if you just I'll write here first step, then I'll go for the last step directly, that is nothing but C dash D dash into 2 by 3, and here we'll get on behalf of G it is H is there, H dash, on behalf of I it is J is there. Okay, so finally I'll write this answer, that is nothing but 2 by 3 L into HFT. Okay, see both answer will be similar. Okay, here I have written L, there I have written L dash. Anyway, so finally we can write the area of the indicator diagram. Area of the indicator diagram is nothing but I can just write the total value here, like first one I got HS plus SD and into this one into L plus this is first one, second one I can write here, this is 2 by 3 L into. So if you want to write L dash or only simple L also you can write, because stroke length is there, you can just write L also. So L into HFS plus here we'll write this is 2 by 3 L into HFD. So if you see everywhere L is common, so we can write like HS plus HD and this is plus 2 by 3 HFS, and here we can write 2 by 3 HFD and whole bracket we can write here L is a common here. Okay, this is our area of the indicator diagram. But previously, one more time again I'm reminding you that we have identified that work done by the pump, the work done by the pump is proportional to the area of indicator diagram. This one already we have proved previously, area of indicator diagram. Okay, so there what we have written, what are the work done is there that we have identified. Work done by the pump per second, work done by pump per second is directly proportional to the area of the indicator diagram. So what I can write here, so this one, let me write work done by the pump is directly proportional to the same value here, like HS plus HD plus this is 2 by 3 HFS plus 2 by 3 and this is HFD, this is D. Okay, and whole brackets I can write here L. Okay, now yeah, same thing, just I'll write here by removing this proportional. Let me write here into K and into L of this all this whole term, like HS again and HD plus 2 by 3 HFS again plus 2 by 3 this is HFD, the whole term. Let me write here. So what is the K value here, or what I have taken? This is nothing but the constant of proportionality, constant of this is proportionality. Okay, so this is about all these things. Now we know that we can write the work done equal to, this will be also we can write like rho GAN by 60. Okay, this is for the single acting reciprocating pump. Okay, for the double acting reciprocating pump we can write, for the double acting reciprocating pump we can write actually here this is not the work done, the K value what we have taken actually there. Okay, the K value what we have taken for the single acting reciprocating pump, this one, and for the double acting reciprocating pump the K value will be like 2 rho G AN by 60. This is for double acting, this is for double acting reciprocating pump. So similarly, just I can write here. So if you will write the final one, what is the work done by pump, what is the work done by pump per second for single stroke reciprocating pump, then I can write this like this value, K value, that is nothing but rho GAN by 60 and hold this bracket of this value like HS plus HD and plus this is 2 by 3 HFS and plus 2 by 3 HFD. Okay, this is for single stroke. Similarly for the double acting single acting, this is not single stroke, this is single acting. Okay, similarly for the double acting will be same manner will be there. For the double acting reciprocating pump, just 2 will be multiplied here along with this whole all these things. So this is all this value what we require to identify. Okay, let me write here, otherwise we 60 and divided by HS plus HD plus this is 2 by 3 HFS again 2 by 3 HFD. So this is all about the equations for the work done by the pump per second in the for the single stroke single acting reciprocating pump and for double acting reciprocating pump. I hope you understand this lecture. though it is a little bit lengthy, but the equations, like few things we need to remember and few things we need to derive from the previous one. Because I have taken the help like what we have discussed previously, the work done part. And the equation also, what I have shown you, like this also already derived previously. If I combine all the things, then it will take like more than 1 hour lecture will be there. That's why I've taken directly from the previous lectures. I hope you understand. Still, if you are having any doubt and query regarding this, you can give a comment on the comment box. Thank you all.